All right, for this lesson, we're being introduced to the normal distribution, which is a pretty important aspect of the statistics and probability unit. And in general, if any data is distributed normally, it always has a characteristic like this. We call a bell curve shape, in which it's symmetrical. It's always symmetrical about the mean, which means the mean is also the median, which is also the mode. It's the highest point. And there's various elements of it that are always standardized. For example, that if we're looking at between plus and minus 1 standard deviation from the mean, that always represents roughly 68% of all the data is within that. And as we go down more standard deviations, we can see what I've highlighted here. If we're within plus or minus 2 standard deviations of the mean, that means about 95% of the data. Plus or minus 3 standard deviations from the mean, that's virtually everything, 99.7% of the data. So the vast majority of the data of something that is a normal distribution is within plus or minus 1 standard deviation of the mean, roughly 68%. So with that said, we can also do a number of things with our GDC, but let me get to this first question. The number of chocolates in a bag is normally distributed such that, what this means here is that the first value is always the mean. So I'll write this down here where the mean is 43. So on average, there's 43 chocolates in a bag. And the second number is always the standard deviation. Sorry, that's wrong. The second number is always the variance. And so keep in mind, variance is lowercase sigma. However, what tends to be more helpful is to find the standard deviation quite often. And so the standard deviation, recall, is always the square root of that. And so I just realized the variance, there, that's variance. I really want to write down standard deviation. And that's because, like I said, it's actually what we use more. So if the variance is 9, that means the standard deviation must be the square root of 9, which is exactly 3. So that's actually something we'll end up using more often. And so I want to use this to find the probability that there are more than 37 chocolates in a bag, knowing that it's normally distributed, the mean is 43, and the standard deviation is 3, or the variance is 9. So one option is to use no technology at all, but to use this sort of data and some problem solving that I mentioned here. And so let's make a rough little sketch here of what this normal bell curve would look like. It's symmetrical, it goes up, reaches a peak, and comes back down. Okay, I know the mean is 43, so right in the middle. This is 43 chocolates. The standard deviation is 3 because the variance is 9, which means every time I go up 3 chocolates, 46, 49, and so on, I go up a standard deviation. If every time I go down 3, 40, 37, again, I'm going down 2 standard deviations. And so this 37 we're trying to find right here represents the probability that there's, or actually, sorry, I should say more than 37, means I want to look at what's the probability that we look at a bag that's part of this region here. What's the probability the data is in this big region, which would be a pretty high probability. So how can we calculate this? Well, what I'm really asking is to find the probability that X is greater than 37. Now, whether I say 37 or 30 greater than or equal to doesn't really matter because this is continuous data here. While actually the number of chocolates isn't continuous, we think of a normal distribution as being continuous. So quite often, whether we have this or this, it's interchangeable. But I do say more than 37. So one way to figure this out is to look at this and realize, okay, this curve is always symmetrical, which means all of this must be half. So this must be half the data, which means 50% of all the data is here. So I just need to figure out what's here, which is, notice these are standard deviations of 3, which this is the region 2 standard deviations below the mean. If I look back up here, I had this highlighted before, that whenever we're within plus or minus 2 standard deviations of the mean, that is roughly 95% of the data. Well, I'm just looking at half of that, because that 95% is from here to here. I only want half of that. So if I look at this chunk right here, that region there must be half of 0.95. And keep in mind, this is all actually rounded. It's not exactly 0.95. And so that's approximately 0.0475. And so roughly 47.5% of the data is between 37 and 43. Exactly 50% of the data is above 43. So put the two together, the probability that a randomly selected bag has more than 37 must be 0.475 plus 0.5, which is 0.975. So a 97.5% probability that a bag will have more than 37 chocolates. So that we could figure out visually from using some of the characteristics of normal distribution curves right here. Another option is use our GDC, which we kind of have to use it if we're not given data or values like this that just happen to be right on a standard deviation. So this we need to be familiar with your GDC, and quite often on most GDCs, they call it the normal cumulative distribution function. And so this is the function we tend to use the most. And to use this on our GDC, we need to know a few things. We need to know the lower bound, which in this case is 37, the smallest number. We need to know the upper bound, which in this case, there is no upper bound. This, theoretically, this curve goes on forever. Realistically, it doesn't. You're not going to have billions of chocolates in a bag, but theoretically it does. So the upper bound for most GDCs, we just put in a large number. For example, you just go 10 to the power of 99. That's generally the biggest number most calculators can handle. We need to know the mean, which again is 43, and we need to know the standard deviation, which is 3. And you type that in, and you should get actually a more accurate answer compared to what we did before. And you should get this probability of there being more than 37 to be approximately the 3 significant figures, 0.977. Small difference. That is a bit more accurate. And then you were always allowed to use our GDC. So this normal cumulative distribution function is one we'll use a lot. It essentially just does the work for us once we know what we're looking for. All right, so over here in US dollars, the 100 movies that grossed the most money had a mean of $491 million US and a standard deviation of $379 million US dollars. If we assume the amounts are all normally distributed, let's assume the amounts are all normally distributed. So with that said, let's say we select a movie at random from this list of 100. Well, what's the probability of this first one? What's the probability that the movie grossed less than $870 million? So we have a few options for this. One is to notice that 870 is actually not a random number. One is to note that 870, that's a weird looking 870 is exactly our mean, 491, plus 1 standard deviation, which means we're looking 1 standard deviation above the mean. So we could figure this out by figuring out what I did before, which is to realize, okay, if I look back at this, we're actually trying to figure out everything from here down. And I could figure it out logically in a similar manner that I did here. However, since I've already done something like that, well, that's not wrong. We might as well, I'm just going to go to my GDC here. And so for this, we just need, if we use our normal cumulative distribution function, we need to know the mean, which is, again, 491. Need to know the standard deviation, which is given to us again, 379. We need the lower bound, which in this case, there kind of is no lower bound. It's anything less than 870. So in general, I wouldn't put a 0, even though you may go, well, a movie can't have less than a 0 revenue, and you're right. But again, for using a model, I would just, half of numbers are all negative. So just to be safe, go negative 10 to the power of 99. In fact, I think actually on many of the calculators, the default it gives you is -1 times 10 to the power of 99. I think that's the default quite often it puts in. So just an incredibly small number, but again, negative. And then the higher bound or the upper bound, in this case, is 870. And then we just calculate it, and we get approximately 0.841. So approximately 84% of these movies made less than $870 million gross. For the next one, I want to find between 500 and 600. Well, I can do the same idea. Really, it's going to have the same mean, the same standard deviation. I just need to change the upper bound and lower bound. And the upper bound will be 600, the lower bound will be 500. This will be quite quick. And so you should pretty quickly get to approximately 0.104, a little more than 10% of the movies. And lastly, what's the probability that a movie has a gross more than 1,000 million, which is a billion? And there's several options. You could use your lower bound being 1,000 and your upper bound being just 10 to the power of 99. Or just because there's always other options, you could also realize you could go 1 minus the probability of this being less than 1,000, in which you would go 1 minus and use 1,000 for your upper bound and negative 1 to the times 10 to the power of 99 for your lower number. It's all the same thing. In the end, though, it should be pretty quick, but it doesn't really matter. We should get about 0.0896. So roughly 9% of these movies surpassed $1 billion in gross revenue. All right, so notice very little work shown here because really it's all meant to be used in your GDC, which we want to be familiar with. With a bit of practice, it is quite quick. The only kind of annoying thing is sometimes your lower bound, you have to put some obscenely large negative number in, or your upper bound, some obscenely large positive number, but that's not really that annoying either. All right, lastly, sometimes we have to look at our cumulative distribution function backwards, the inverse of it. And that'll come into play here. But first, the actual volume of a 2-liter bottle of Coca-Cola varies from bottle to bottle with a normal distribution, where they say V is the volume, 2,000 is the mean, 4 squared, so 16 is the variance. And quite often variance is shown as the standard deviation squared. And so knowing it's a normal distribution, I know that 2,000 mean is, so 2,000 is the mean, and 4 is a standard deviation, which is what we'll actually end up using more. All right, so if a bottle has less than 1,995 milliliters, it is considered underfilled. What is the probability that a randomly chosen bottle is not underfilled? Which means it is, has more than 1,995. And so essentially, that's what I'm trying to solve. I'm trying to find the probability that the volume is greater than 1,995. And so for this, I can use my normal cumulative distribution function, in which, again, the mean will be 2,000. The standard deviation would be 4, because, again, that 4 squared you see up there is the variance. The lower bound would be 1,995. And the upper bound is the biggest number your calculator can handle. It doesn't really, if you put in 10 to the power of 10, it'll still give you the same answer in the end, because realistically you're not going to have a bottle of Coca-Cola that has billions of liters inside it. But just put a large number in and you should get out your answer, which should come to approximately 0.894, just shy of 90% are not underfilled, which you could say that means 90% are properly filled. Except we also have the other side, which is sometimes they could be extremely overfilled. And by definition, it's saying the top 1% of these volumes are considered extremely overfilled. So what is the minimum volume that would be considered extremely overfilled? So for this, let's think about what we're trying to find here. Let's visualize a normal distribution here. Again, so I have my curve go up and down. We know the mean is 2,000. We know the standard deviation is 4, but I'm not going to label those. The vast majority of these bottles are not extremely overfilled, but they're just the top 1%, which means of all of this here, I just want to imagine the highest 1% of what I have shaded there, which as a little visual, let's say it's like right here, just this little chunk, which technically does go on forever. Theoretically it goes on forever. Realistically, it doesn't. And I'm trying to figure out what number that is. That's what we're trying to figure out. What number would go there so that this is just 0.01. We know the area is 1%, but what number would go there? And so maybe instead of a question mark, I'll put an X, which means I'm trying to solve the probability where the volume is greater than X, but I know that probability equals 0.1. And so I need to use my normal cumulative distribution function backwards, or the inverse, I should say. And so on most devices, the TI-84, for example, this is called the inverse normal. And which you have to be asked a few things. And so for this, you have to know the area, which is really the probability. But again, keep in mind that probability is really being, is represented by this area, and vice versa. This area over here represents the probability of 1% of these bottles. And so the area is 0.01. We need to know the same standard deviation in the mean. So that's the same as before. I don't need to change that. We also need to know, are we have a tail to the right, left, or center? So what does that mean? Because even though we know the area is 0.01, the calculator needs to know, are we looking at this chunk, or are we looking at this little chunk over here? And so we call that the tail. And as you can see, the part I'm looking at is to the right. So we want the tail to the right. Alternatively, you could get the same answer by looking at all of this, which is 99% of the data. And then you could, say we want the area to be 0.99, and then we'd have our tail to the right. Because we're still trying to find that x, but we know everything to the, sorry, I get my rights and lefts mixed up a sad amount of time. This would be a tail to our left, because from that x, we'd be looking at everything to the left of it. However, though, I don't want to needlessly make this more work than it has to be, so I'll stick with what I had originally. Plus, then I don't get my rights and lefts mixed up. And so just input this data in, and it should tell you the value of x, which is about 2009.3, so to three significant figures, 2010 milliliters. So anything 2010 milliliters and above to three significant figures would be considered extremely overfilled. And keep in mind, for all of these, like I was mentioning before, there's always multiple approaches, especially when you realize the entire area of every single probability of a normally distributed probability curve is always 1. So quite often, if you don't want to find it directly, you can go 1 minus something. But I found everything, so I'm done.